So once again, hello everyone. And I'd like to present you the project I've been working on here at CERN for quite a while, which is Adaptive Perf. So let me start by explaining what Adaptive Perf actually is. So it is an open source code profiler for Linux, based on Linux Perf with our own custom patches, and developed in the context of the CyCops project, which I will talk about in just a few moments. It's a profiler which samples both on CPU and off CPU activity for single-threaded and multi-threaded applications. And in case of multi-threaded applications, it traces every spawned thread and process along with the hierarchy of spawning, which I will show in the live demo and also in a few moments. Compared to original perf, Adaptive Perf minimizes risk of broken profile stacks for programs compiled with frame pointers by detecting inappropriate kernel and CPU configurations automatically. And what I mean here is, for example, checking the presence of NUMA, non-uniform memory architecture, and checking the appropriate kernel settings, such as perf event max stack and perf event paranoid. And Adaptive Perf produces interactive flame graphs and charts viewable in a web browser, as you can already see on the screenshots here on the, let me just see the cursor. Yeah, on the screenshots on the right. And by a flame chart, I mean a time-ordered flame graph. So basically, Adaptive Perf produces non-time ordered and time-ordered flame graphs. And the main functionality, which is on CPU and off CPU sampling, is designed with hardware portability in mind. So you are not constrained to any single computer architecture or any single CPU vendor. And Adaptive Perf has already been successfully tested on x86-64. RISC-V is currently in progress when it comes to testing, but with RISC-V we are nearly there. And ARM64 is planned when it comes to testing very soon. And Adaptive Perf doesn't only just sample on CPU and off CPU events. It supports custom sampling-based perf events for profiling more intricate interactions with hardware, such as cache misses or retired instructions, as long as it's supported by perf itself. And also, our profiler allows TCP streaming of profiling data to a separate machine for real-time processing. So you can run a profiler on one machine, and then connect another stronger machine to it, so that the heavy processing tasks can be done by that stronger machine instead. But you will also see the most detailed diagram of how Adaptive Perf works on the next slide. And there is one important note: Adaptive Perf is not a continuous profiler, so it's meant for profiling single commands only, and it's definitely not meant for standard data center 24/7 monitoring. And because of that, the main target audience of Adaptive Perf is software and hardware developers who optimize their software and or hardware, also as part of software-hardware co-design. So let me talk now about how Adaptive Perf works under the hood. So there are several parts. First of all, you have the Adaptive Perf frontend, which is the command line tool, which configures and runs Linux Perf in a way such that it streams TCP data through its Python API to the backend called Adaptive Perf server. And Adaptive Perf server does all the heavy processing of perf events. So it analyzes the periods, it constructs flame graphs on the fly, etc. And as the result, it produces files for a separate viewer called Adaptive Perf HTML, which in turn displays an interactive website here. But this is how Adaptive Perf currently works. But there are extension plans. So in the future, Adaptive Perf may also work with other profilers or interfaces, such as PAPI. PAPI in order to support more devices, especially non-CPU ones like GPUs. And also in the future, there will be a separate library called Adaptive Perf Analysis with the API, so that you can analyze the profiling results basically in more ways than just by looking at visual flame graphs. And last but not least, Adaptive Perf Server, Adaptive Perf HTML, and the future Adaptive Perf Analysis can be run on a completely different machine, as already mentioned, without any of the profiled programs, without any debug information, debug symbols, etc. It's you can just run it on a completely unrelated machine, let's say, unlike Perf script, for example. So before I move on, let me talk briefly about Cyclops. So Cyclops is an EU-funded project about hardware acceleration with open standards using CICL and RISC-V. And this includes also producing customized RISC-V cores and including vector extensions in RISC-V. And you can check more details about the project at this website. And CERN is involved in this project in two ways. So the first task of CERN here is implementing CICL support in root and cling and demonstrating that support on a Lorentz vector calculation example. And this is done by our colleagues in the EP department. And the second task, which is done by us, is benchmarking and profiling along with integration testing of all use cases envisaged in Cyclops. And these use cases, apart from root, are genomics analysis and autonomous systems. So as you may have guessed already, Adaptive Perf is part of task 2, but its applications extend well beyond Cyclops. So it can potentially be used for online and offline computing at CERN and other physics experiments. So if you want to profile, for example, MATGAP5 or GEANT4, you can do it. It can also be used for software hardware co-design, for example, in heterogeneous computing and development of triggering and DAQ systems at the LHC experiments. But these are just the very obvious CERN-related examples, but software profiling is a field which has much more applications than just this. So you can try Adaptive Perf already now. It's open source, and you can get it for free from our GitHub here. And it's currently available as a development version. So all feedback and feature requests are more than welcome. And essentially there are three parts. Adaptive Perf, which is the main thing, consisting of the command line profiling tool and the server, so front and back end. And this is licensed under GNU GPL version 2. Adaptive Perf HTML is the second part, and this is the web server for displaying profiling results. And this is licensed under GPL version 3. And there's also the third part called Linux, but don't be fooled here. You don't have to do any kernel patching or custom kernel installations here. It's basically the Linux kernel source tree with patched perf. And it has to be the full source tree because of the way the perf source code is structured, unfortunately, which is outside of my control. And this is stored temporarily on CERN GitLab because of some issues with file size limits when pushing to GitHub. Hopefully it will be sorted out soon. And this is licensed on the same terms as the vanilla Linux kernel. So just a quick starter with Adaptive Perf. So there are instructions on GitHub how to set up this. So you need to install Adaptive Perf and Adaptive Perf HTML there. You need to pay close attention there to the kernel settings and information about NUMA. And this is also part of the automatic detection of incorrect configuration by Adaptive Perf. And afterwards, profiling any command can be just done with this single command. Adaptive Perf followed by command to be profiled. And it is, you must quote it. You must quote it if it has spaces. If it doesn't have spaces, it's not strictly necessary, but still recommended. And after running this command, you need just to wait until it finishes and produces the results directory. And afterwards, you can use Adaptive Perf HTML to view the profiling results. And this is done by firstly setting the Flask profiling storage environment variable to the results path, then running Flask, which is a Python web framework, and pointing it to Adaptive Perf HTML which is this. And afterwards, you just need to open the website and you are done. You can start exploring. So let me just now quickly demonstrate Adaptive Perf, how it really works. So let me just switch to my laptop. Let's see. Okay. So let me just go quickly here. So currently I'm on the yes. So I will just see how I can. Okay. So I'm currently logged in to one of the x86-64 test nodes with an Intel CPU, and I have this very simple C code, which is a multi-threaded program just doing some function calls between first func and second func, along with recursion. And what I will do is compiling this program with debug info and with frame pointers to produce the program called, let's see, test PRG. What's going on? Okay, typos. It's no omit reframe pointer and no omit frame pointer. Here it is. And now I have the command line tool called Adaptive Perf. So let me firstly run the let it print the help message. So there are several customization options you can use for Adaptive Perf. The most important ones here in this case will be this one, which is delegating post-processing to another machine running Adaptive Perf server. So what I will do is I will run Adaptive. Okay, I also need to increase the font size. So I will run Adaptive Perf server here on this machine on my laptop, and then I will make the test node here connect to Adaptive Perf server on my laptop, so that profiling data can be streamed in real time. So this is this option, and I will also use this option to specify an extra perf event to use in addition to standard on CPU and off CPU profiling. So in this case, I will use page faults, which is a kernel-based event rather than a proper hardware-based one. So let's run it. So it's page faults 1. So the first entry is basically the name of the event as stated in perf list. The second entry is the period. So if you enter, for example, 5, Adaptive Perf will instruct perf to make samples on every 5 occurrences of such an event, and you can pick whatever number you wish here. And the third entry is basically the title of the event to be shown at the on the website later on. And now I will also set up put the address of Adaptive Perf server, port 5001. So in this case, I have put the localhost address because I use SSH remote port forwarding here. So I'm pretty sure this will work. And now I will just do this program, and let's go. So the code itself will run for approximately 60 seconds. In the meantime, I can explain the messaging here. So yeah, the very first part is just GPL stuff. Then the first stage of Adaptive Perf is checking system configuration. So it checks if appropriate prerequisite programs are installed on the system. It checks the kernel parameters, etc. Then it checks the CPU specification to make sure that the profiled program can be isolated from the profiler and potentially post-processing itself. so that as little interference, so we have as little interference as possible. Then it checks for NUMA, and then it prepares the necessary directories and runs profiling itself. So you can see that it has successfully connected to Adaptive Perf server. The code has just finished executing, and the results have just been processed. So yeah, the code was executed in 52 seconds approximately, and the entire session, the entire profiling run lasted about 57 seconds. So what I can do now is I can go to the Adaptive Perf website, which is already up and running locally on my laptop. So yeah, you can see that yeah, I have run several profiling sessions before. This one is the newest one. You can see that we have test PRG run on Cyclops Gen 2 Profiling 1 on this date and at this time. So let me just open this. And now you can see the time value here. And on the left, you have the, yes. So let me just see. Okay. So going back to the timeline view. So you can see on the left that you have a thread tree, which can be expanded or collapsed as you wish. So I will, because this is a very simple program, I will expand all threads and processes. And you can see that yeah, we have several threads here, and you can see red and blue blocks. So red blocks correspond to on CPU activity. So basically, this is the time when a specific thread or process was actively running on the CPU, and blue parts are off CPU. So this is the time when the specific thread or process wasn't running on the CPU because, for example, it was waiting for I/O, or it delegated processing to a GPU, or it was blocked because for example of lock contention. And what you can also do here is you can check the spawning stack trace of every thread or process except for the root one by right-clicking the thread you are interested in. So, for example, this specific process thread ran for exactly 48,728 milliseconds, point something, and the sampled time as sampled by Perf, because remember that we are talking about sampling-based profiling, which is not 100% accurate. So the sampled runtime is about 48,725 milliseconds. So the difference is not large here, and you can see the spawning stack trace of this thread, which also includes kernel-specific functions. And yes, you can do it for any thread or process you like. And in order to open flame graphs, you need to double-click a thread or process you are interested in. So this is one example. So I can resize this flame graph so that more space can be used. And this is a flame graph for wall time in nanoseconds. This is the main flame graph, which is about on CPU and off CPU profiling. This specific thread didn't have any off CPU activity, so you will not see any off CPU related stuff. But for on CPU, you have the same thing you have in your standard flame graphs. And what you can do here, you can zoom in, you can zoom out, you can do search as you type. And the search box also supports regex. So I can do, for example, search for everything starting with first or second. And you can then see that we have these blocks matching. You also have time ordered flame graphs. So when I tick time ordered, then the blocks are rearranged so that the time order is so that everything is time ordered. And you can see that a new block has appeared called compressed. And this is because blocks taking, as the message says, blocks taking less than 2.5% of total samples and by total samples, I mean the number of samples here in all, are not shown essentially to speed up rendering, because in some cases you can have so complex flame graphs with very deep, so deep stacks that rendering this can be very time consuming and work consuming, and can, in extreme cases, it can make your computer freeze. So this is basically the safety mechanism for avoiding this, but this can be adjusted basically by changing this number. So if you want anyway to see more detailed information on your flame graph, and you are happy that your computer will manage to render this, you can decrease this percentage. So for example, I can decrease it to 1% and then open the flame graph again. And now you can see you start having more details. So you can see that we already start having some first func blocks, second func blocks, etc. But this is still interleaved by compressed blocks because I didn't decrease it to 0, I decreased it to 1. But if you are feeling brave, you can disable this mechanism altogether. And I already know that for this flame graph, my computer will manage to render it. But for example, I've tried rendering a flame graph for some root snippet, and well, just to make it short, it didn't end well. So, but in this case, you can see that we have now many tiny narrow blocks indicating to probably either, let me just zoom it in, probably either first func or second func, as you may have guessed from the test code. And also, what you can do is also not just looking at on CPU and off CPU flame graphs. You can look at, in this case, at page faults. So in this case, it's a very simple flame graph. Just this thing indicating that we have one page fault. But if I, for example, go here, and in this case, you can see off CPU activity on the flame graph. This is indicated by blue blocks rather than red ones. And now let me just go to page faults. And now you can see more information about page faults here. So the number of samples here corresponds approximately to the number of page faults. And you also can see a few compressed blocks, meaning that the safety mechanism has already done its job. And you can also do time ordered thing here. Yeah, and you can also do search as usual. Nothing too different here. The time axis itself is in milliseconds. And there's also one useful thing about Adaptive Perf HTML. It warns you automatically if the difference between exact and sampled runtime exceeds specific percentage. By default, it's 50%, but you can adjust this percentage as you like. So, for example, if you are happy with the difference being larger, you can increase it to 75%, 90%. If you want to be strict, you can decrease it to 10%, 20%, 5%. I will show an example using some root snippet I profiled a month ago. So let's just wait until the results load. So you may already guess that this is going to be more complex. So you can also see that on CPU and off CPU activity is also more nuanced. And let me open this flame graph. And you can see we already have more deep flame graphs with compressed blocks, and same for time ordered. And let me just quickly check this one. So for example, here you can see that the difference between exact and sampled runtime exceeds 50%. And this is indicated by firstly, turning the sampled runtime into red, and by printing a warning message when you open a flying graph corresponding to the process or to the thread, saying that the difference between the exact and sampled runtime is this and this percentage, which exceeds 50%. And usually when you have this difference, the best solution is trying to increase the on-CPU or off-CPU sampling frequency, depending on whether your thread or process runs mostly on or off CPU. Okay, so I think that's pretty much everything I wanted to show when it comes to Adaptive Perf, Adaptive Perf demo. So let me go back to the presentation. Okay, so here you have also some screenshots of Adaptive Perf. So for example, the command line tool, Adaptive Perf HTML. So I will skip these slides. So at this point, you may wonder how Adaptive Perf compares to other similar and maintained profilers. So here's a comparison table against, I believe, the most popular choices when it comes to program software profiling. So we have Original Perf, Intel Vitium Profiler, AMD UProf, Valgrind, gProf, gPerf tools, and NVIDIA profilers such as Nsight Compute and Nsight Systems. So essentially, Adaptive Perf is hardware vendor portable. It does profile software-hardware interaction if supported by a user's hardware architecture. It has low profiling overhead thanks to sampling-based profiling. It's open source. It does off-CPU profiling. And it will have heterogeneous architecture support in the future. And compare it, for example, to Original Perf, which has limited off-CPU profiling. And by limited, I mean it can only produce summarized information about off-CPU activity. So for example, you don't have any exact timestamps of CPU events. You only have information that this specific stack trace spent in total 5 seconds outside of CPU, but you don't have any other information. So Adaptive Perf provides more information here. And Perf, as far as I know, doesn't support heterogeneous architectures whatsoever. Intel Vitium Profiler, well, the biggest disadvantage is that it's Intel. So you must use Intel CPUs for profiling with Intel Vitium Profiler, and it's not open source. And for heterogeneous architectures, again, it just runs on Intel. So just Intel GPUs or FPGAs. AMD UProf suffers from similar disadvantages, only AMD CPUs and GPUs. It's not open source either. Valgrind, on the other hand, its overhead is so large that profiling large code bases doesn't make sense. And it doesn't profile software-hardware interaction. It doesn't do off-CPU profiling, not to mention heterogeneous architecture support. Similar for gProf and gPerf tools, but in addition to Valgrind, they require specific code instrumentation other than just merely compiling with frame pointers. And NVIDIA profilers, well, it's also just NVIDIA. It's not open source. It doesn't even have low profiling overhead. So from experience, when I tried to profile programs running on NVIDIA GPUs with Nsight, the time overhead at least was significant. So you can see that Adaptive Perf is a promising choice here. And now let me finish off with talking about the future plans for Adaptive Perf. So as mentioned several times already, we want to implement profiling heterogeneous architectures and non-CPU devices in a maximally open source way. It may not be possible, but we will try our best, of course. And one idea of doing this is through this thing called PIPI, which is a programming interface abstracting away access to performance counters. And it's open source, and it supports several CPUs and GPUs, including both NVIDIA and AMD. So this looks like a promising choice, but we need to investigate how feasible integrating this into Adaptive Perf is. We also want to apply Adaptive Perf to cache-aware roofline proof of modeling and potentially RISC-V core customization by collaborating with some of our Cyclops partners, namely INESC-ID in Portugal, Codasib in Czech Republic, and Eurocom in France. We want to expand the analysis functionality of Adaptive Perf by making a separate library with the API, as mentioned at the beginning, and also by adding the plugin API to Adaptive Perf HTML, so that everybody can extend Adaptive Perf HTML and its visualization options at least easier than forking the repo and submitting a TR afterwards. Also, as part of good software development practices, we are currently setting up automated tests, which will be integrated into our CI pipeline. We want also to add profiling on a lower level and with more debug information. So, for example, we want Adaptive Perf to show line numbers, also perhaps go down to LLVMIR, MLIR, or assembly, wherever applicable, etc. Also, we want to make Adaptive Perf download debug info automatically for a given process if it's not present, because you cannot always have debug information locally on the machine. And this can be done, for example, through debug info-D, which is a server providing debugging information, and there are public centralized ones available here. We also want to match non-sampling based metrics from Perf and or other programs, for example, power consumption, CPU, GPU temperatures, network bandwidth, etc., to code segments in a similar way, perhaps in a similar way to what Adaptive Perf currently does. And we will have an open lab summer student coming here to CERN on the 1st of July to work on this. So we will investigate it together, how to do it in the most efficient way. We may try to decrease profiling overhead even more, for example, by replacing Perf's Python API with its compiled language equivalent like C, C++, Rust, etc., you name it. But this may require another set of Perf patches in addition to what we've already done, because Perf out of the box just supports Python and Perl, which are both scripted languages or interpreted languages. We also want to see if the frame pointer compilation requirement can be weakened or removed altogether. So, for example, these guys from Polar Signals did some very clever dwarf processing in a more compact way than what Perf currently does. And by doing this, they managed to obtain stack traces without compiling with frame pointers. And their software is open source, so we can look into it. And the good news is that maybe full removal may be unnecessary, because more and more Linux distributions started shipping packages with frame pointers included by default. This is the case with Fedora. This will be the case with Ubuntu. As far as I know, this will also be the case with Arch Linux. Let's hope that other distributions will follow suit here. But of course, any other suggestions, any other feedback is more than welcome. Okay, so yeah, that's the end of my presentation. Thank you very much for your attention, and I'm open to questions if you have any or comments.
Thanks a lot, Max. Are there any questions to Max? No. Any questions from remote? Oh, Charles, yes, please.
Hi, thanks for a very interesting talk. So I have a couple of questions. First of all, can you get it to instrument just a small section of code? So for instance, you start your program with the profiling paused, and then you put in some kind of triggers around an interesting section in your code and have it just instrument that?
It's a very good question. This is not currently supported by Adaptive Perf, unfortunately, but we want to look into adding it in the future.
All right. Can you also do things like look at cache misses and much lower level stuff like that?
Yes, absolutely. As long as original Linux Perf supports it, you can do it. So, for example, on my laptop, I can do profiling with cache misses or retired instructions or branch misses. Basically, as I said, if perf supports it, adaptive perf should support it as well automatically.
All right. The other thing which kind of worried me was when you said that you have to have a very, powerful CPU to be able to view complex profiles. And you had to change the fraction that was displayed. It sounds like it's trying to load the entire profile all at once, as opposed to, if you try to zoom in on one section, just load what is in that section. Is that correct?
So what you are saying is more or less correct at the moment, and it's a limitation of the JavaScript library we use for rendering flame graphs. Basically, compressing flame graphs in the way I showed in this talk is our first attempt into mitigating this issue. But we may also look into other solutions here. But these flame graphs are loaded once per thread or process. It's not like everything is loaded for all threads at once. So at least this is one good news I can share with you here.
Okay. Yeah. So, I mean, what I've seen other profilers do in situations like that is it basically loads only, what is kind of visible at the level of zoom that you are looking at. As you go deeper and deeper into, smaller and smaller time segments, then it will actually go and load more information. So this way it doesn't overwhelm the browser or, whichever.
Yes, the approach you are describing makes a lot of sense to me, but unfortunately, yeah, the JavaScript library we use has its own limitations, and unfortunately, it has to be the way it is at the moment. But as I said, we will look into other solutions of mitigating this issue, so that you can basically be able to analyze more complex flame graphs without larger issues, essentially.
All right, thank you.
You're welcome.
Thanks. Are there more questions to Max? Guilherme, please.
Hi, Max. This is Guilherme. Nice talk. I wonder if you want to contribute these custom patches you said you have for perf for improving the off CPU sampling directly upstream.
Yes, there are plans of doing it. So I want to contribute all of the patches we've made to upstream. We just need to figure out the best way of testing these patches and submitting them to the appropriate mailing list.
I see. Another thing, one thing was not very clear to me. Are you processing the perf data directly? Are you using perf script, or are you converting it to some other format and then loading with your JavaScript library?
So essentially how it works is that all perf data is streamed in real time to Adaptive Perf server, and then Adaptive Perf server converts these results into the format which is perf independent and can be read by Adaptive Perf HTML, for example, so that you don't have to have perf installed on another machine. You browse the profiling results in, and theoretically it doesn't even have to be Linux. It can be Windows or
so
Mac,
you're not writing to disk then the perf data.
So yes, perf.data is not written to disk. It's streamed directly into Adaptive Perf server.
Interesting. Have you considered
sorry, just one thing. More specifically, how it works is that perf.data is streamed into perf's Python API, still on the profiling machine's sites, and then it's some pre-processing is done on that site, and then it's streamed in real time into Adaptive Perf server for further processing. But yeah, as I mentioned, no perf data is saved into disk at any stage.
I see. Okay, very interesting. I wonder if you looked into the SQLite conversion from perf, that you could write to the SQLite from a perf.data and then just process it at the end.
This is something which we may check out at some point in the future.
Okay, sorry for the battery of questions.
No problem.
Very interesting.
Thanks a lot. Are there more questions to Max? Yes, Matti, please.
Yeah, hi, thanks for the interesting talk. So one challenge that we have in CMS had with the plethora of CPU profilers is that, so we use the TBB for multi-threading. What at least nowadays tends to happen there is that, I mean, let's say how TBB sort of has this notion that there is the sort of the main thread and then there are the worker threads. At least in the way how we use it, it's really that we treat all the threads as the same, but this is not really how the situation looks for the, like in a straightforward way for the profiler. And what we like typically would see like in the flame graph is that there are these call stacks. One bunch of them gets associated to the worker threads, and then another set is then associated to the main thread, whereas what we would like to see is that these are all like kind of merged or stitched together. We know that Intel vTune does that. We patched the sort of older in-house de facto unmaintained IG-prof to do that. Do you have any sort of experience on let's say using this profiler with the TBB-based applications?
So we haven't tested Adaptive Perf with TBB specifically yet. I mean, if TBB spawns new threads by using appropriate Linux system calls like fork and clone, then I believe Adaptive Perf should capture this without issues. If TBB spawns these threads in some different, more intricate way, then it may produce a similar issue to what you are describing. But yeah, we are more than happy to test it on TBB and figure out how to make Adaptive Perf work with TBB.
Okay, that sounds great. We maybe need to follow up offline. Yeah, I don't myself know all the dirty details here, but what I've understood it as TBB, it does some dirty tricks for the thread launching that then basically, as you said, it makes it difficult for other profilers out of the box to deal with it. Another kind of peculiar behavior with TBB is that they literally move stacks between threads if they want to, kind of like having a coroutine, which I will vaguely recall also confused some tools. But yeah, I think we should give this a try and then let you know what we find.
So yes, we can follow up on this offline. Basically, what we need to do is testing more thoroughly how TBB interacts with Perf and Adaptive Perf, and yeah, decide how to go from there afterwards.
Okay, great. Are there more questions to Max? Okay, I don't see anybody raising his hand at the moment. So it's 3, 2, 1. Okay. Okay, so thanks a lot. Thank you everyone for attending this Computer Accelerator Forum and the Accelerator Forum. So as said, 29th of May, we will have NVIDIA coming. This will be the next one. And thanks everyone for the very interesting discussion. And